We're going to talk about isolated points and limit points. Let's recall some definitions from before. Recall that a set in the form parentheses a comma b, that is the set of real numbers x such that x is larger than a and x is less than b, is called an open interval. Similarly, a set in the form square bracket a comma b, which is the set of real numbers x such that x is greater than or equal to a and x is less than or equal to b, is called a closed interval. Remember our motivating questions. Why do we use these words open and closed? Well, the following proposition allows us to think of an open interval in a slightly different way. Let's say that a comma b is an open interval. Then there exist real numbers p and epsilon such that I, our open interval, is v sub epsilon of p, where v sub epsilon of p is the set of real numbers x such that in absolute value x minus p is less than epsilon. Let's say that A is a sequence consisting of numbers x sub n. Then the limit of the x sub n's equals a number p exists if and only if, given a positive epsilon, we can find the delta such that x sub n is an element of v sub epsilon of p for all n greater than delta. Next, we define an open set. Let's say that capital O is a subset of the real numbers. We say that capital O is an open set if, for any p in our set capital O, we can find a positive epsilon such that v sub epsilon of p is contained in capital O. The following proposition gives the main properties of open sets. First, an open interval is an example of an open set. Second, let's consider an arbitrary family of open sets denoted by capital O sub lambda. Then the union, capital O, over all of the open sets is also an open set. Finally, let's say that we have a finite collection of open sets. Then the intersection is also an open set. Today we're going to build upon these ideas and discuss two main concepts: isolated points and limit points. Let's say that S is a subset of the real numbers. We'll say that a point P is an isolated point if there exists a positive epsilon 0 such that v sub epsilon 0 of P intersect S is the singleton set consisting of P. That is, there exists a neighborhood of P whose only point in S is the point P itself. We'll denote I, parentheses S, as the collection of isolated points in S. We'll say that S is a discrete set if every point P in S is an isolated point. That is, S equals I, parentheses S. Just a caveat here, when we say discrete, we mean discrete spelled D-I-S-C-R-E-T-E, not discrete spelled D-I-S-C-R-E-E-T. We'll say that a point in the real numbers is a limit point for the set S if, given any positive epsilon, we can find an element x sub epsilon and v sub epsilon of p intersect S and x sub epsilon does not equal p. Note that we do not require p be an element of S. We'll also call this point P a cluster point for S or an accumulation point for S. We'll denote L parentheses S as the collection of limit points of S. Here are the main properties about these two sets. Again, let S be a subset of the real numbers. First, S is contained in the union of I of S, the isolated points, union L of S, the limit points. That is, every point P in S is either an isolated point or a limit point. Second, the intersection of I of S with L of S is the empty set. That is, there are no points which are both isolated points and limit points. And third, L of S is contained in S, that is, every limit point of S is a point in S if and only if every Cauchy sequence of elements from S has a limit which is an element of S. Here we have an example of an isolated point. Let's say that S is the set you see here on your screen. It's the union of the singleton set consisting of 0 along with the closed interval from 1 to 2. You can see on the upper left of your screen that we have here a series of red circles, which are just the neighborhoods around 0. You can see that these neighborhoods, that is, these red circles, can be chosen to be smaller and smaller so that the only point of S sitting inside of the circle is just 0. This means that x equals 0 is an isolated point of S. In fact, moreover, you can actually see that this is the only isolated point of this set S. Let's go over some more examples. Let's say that we have a Cauchy sequence, x sub n's, but let's assume for the moment that our sequence is strictly increasing. That is, x sub n plus 1 is greater than x sub n for all numbers n. We're going to show that I of a equals a. That is, every element of a is an isolated point. Indeed, let's choose an element x sub n in our Cauchy sequence A, and let's denote epsilon sub n as the minimum of the absolute value xn plus 1 minus xn and the absolute value xn minus 1. You can see here that we've chosen epsilon small enough so that it's smaller than the distance between xn and its two nearest neighbors, namely xn minus 1 and xn plus 1. Hence, if we take a look at the neighborhood around x sub n of distance epsilon sub n, then the only point in A in this neighborhood is x sub n, hence showing that x sub n is indeed an isolated point. As another example, let's again let A be a Cauchy sequence, but let's assume that its limit p is not an element of A. We're going to show that L of A is p. That is, the only limit point of A is just this limit p. This explains why we're using the words limit point, because it literally is the limit of a sequence. First, let's show that p is a limit point of our sequence A. Well, given a positive epsilon, we can find a delta such that x sub n is an element of v sub epsilon of p intersect A whenever n is greater than delta. This is the idea of being a Cauchy sequence. We can go far enough out in the sequence such that x sub n is as close as we'd like for it to get to the limit p. However, x sub n does not equal p because x sub n is an element of A, yet p is not an element of A. This means, by definition, p is a limit point of A. Conversely, we're going to show that the limit points of A is contained in the singleton set consisting of just the point p. To this end, let's pick a point q that is a limit point. This means if we choose epsilon to be 1 over a power of 2, maybe 1 over 2 to the k, then we can find a point in the sequence x sub nk, which is an element of v sub epsilon of q, but this also means that x sub nk minus q is less than epsilon, that is less than 1 over 2 to the k. So our x sub nks define a subsequence of our Cauchy sequence which converges to q. However, all subsequences of A must converge to the same limit, so we must have q equals p. This is why our limit set only has one element. As another explicit example of this, let's let A be the collection of rational numbers in the form 1, 1/2, 1/3, 1/4, and so forth. This here is a Cauchy sequence that essentially satisfies the criteria that we listed above here on the screen. This means that I of A equals A, that is, every element in A is an isolated point, and L of A is 0, well, the set consisting of 0. That is, that the limit of this sequence is just 0. We'd like to prove the theorem, so first let's prove the first statement. Let's pick a point P in S. We'd like to first take a look to see, is this point P in either I of S or is it in L of S? Well, if P is in I of S, then there's really nothing to show, but let's observe that this means, given any positive epsilon 0, the intersection of v sub epsilon 0 p with S is just the singleton set consisting of p. Hence, if p is not in I of S, then for every positive epsilon, our intersection v sub epsilon of p with S does not just equal to the singleton set. This means that there must exist another element in this intersection, x sub epsilon, which is different from p. But this, of course, implies that p must be a limit point of S, so p is an L of S. This is why S is contained in the union of I of S with L of S. We'd like to show the second statement, that is that the intersection of I of S and L of S is the empty set. So this assumes by way of contradiction that the intersection is not the empty set, and let's choose the point P that is in the intersection. On the one hand, because P is an isolated point, we can find an epsilon naught such that the intersection V epsilon naught of P with S is just the singleton set consisting of P. On the other hand, since P is a limit point of S, then this means that we can find an x naught that is in the intersection V epsilon naught of P with S, and x naught is not equal to P. Of course, these two can't happen. This is why we have a contradiction. Let's show the third statement. First, let's assume that L of S, the limit points, is contained in S. We're going to show that our Cauchy sequence has a limit that's also contained in S. So let's pick a Cauchy sequence A with terms x sub n, and let's denote P as the limit of this sequence. Let's say by way of contradiction that P is not an element of S. Then, winding through the definitions, for every epsilon we can find a delta such that x sub n is an element of the intersection V epsilon of P with S. But because P is not in S, then this actually means that P must be a limit point of S. But L of S is contained in capital S, so P is contained in capital S. This, of course, is a contradiction. Conversely, let's say that our Cauchy sequence has a limit in S. We're going to prove that L of S is contained in S. So, let's pick a point P in L of S. Then for every epsilon that perhaps is 1 over a power of 2, then we can find an x sub n in V epsilon of P intersect S, where x sub n does not equal to P. This means that we've actually constructed a convergent sequence whose limit is P. But this actually does show that P must be in S, because remember, we're assuming that every Cauchy sequence has a limit in S. So if P were in L of S, then we've actually proven now that P must be in S. Let's consider another proposition here that will try to make these limit points a little bit more explicit. Let's say that S is the open interval from A to B. We claim that I of S, the isolated points, is just the empty set, that is, there are no isolated points, and L of S is the closed interval from A to B. That is, the limit points are all of the elements from A to B, including A and B. First, we're going to show that I of S is the empty set. Indeed, let's pick a point from S. Then for any positive epsilon, we can choose the elements x sub epsilon that you see on your screen, where x sub epsilon is in the intersection V sub epsilon of P with S, yet x sub epsilon does not equal P. This means that actually every point P is a limit point of S. That is, they are not isolated. Next, we're going to show that L of S is the closed interval from A to B. First, let's pick a point P in the limit set. We're going to show that P has to be in the closed interval from A to B. Well, for every positive epsilon, we can find an x sub epsilon in the intersection V sub epsilon of P with S, where x sub epsilon does not equal to P. So if this is the case, from the way that we've chosen x sub epsilon minus epsilon is less than P, is less than x sub epsilon plus epsilon. However, because x sub epsilon is an element of S, then we see that A is less than x sub epsilon, and x sub epsilon is less than B. Putting all of this together, we see that for every positive epsilon, A minus epsilon is less than P, is less than B plus epsilon. Since this holds for every positive epsilon, we then see that A is less than or equal to B is less than or equal to B. This does mean now that L of S is contained in the closed interval from A to B. Let's now do the converse. Let's pick a point in the closed interval, and we're going to show that such a point must be a limit point for S. Given a positive epsilon, let's write down the y sub epsilons and z sub epsilons you see on your screen. Well, each y sub epsilon and z sub epsilon is an element of v sub epsilon of p, but we have to be a little bit careful. If p does not equal to a, then y sub epsilon is an element of S. However, if P does equal to A, then we can actually switch over and look at Z sub epsilon, and this here now we see is an element of S. So this means that in either case, there exists at least one X sub epsilon that is in the intersection V sub epsilon and P with S, and X sub epsilon does not equal to P. So this actually does show that P has to be in L of S, showing that the closed interval is contained in L of S. As a remark, we stated this proposition for the open interval from A to B, but actually we could have proved the same thing essentially using the same argument for the closed interval from A to B. That is that the interior points is the empty set and the limit points is the closed interval from A to B. Finally, I'd like to introduce the concept of closed sets. Let's say that S is a subset of the real numbers. Recall that in a previous lesson, we introduced the idea of the interior of a set S. This is the set of points such that there exists some positive epsilon where V sub epsilon of P is contained in S. Next, we'll say that S is closed if the collection of limit points is contained in S. The closure of S is the set S bar, which is the union of S with its limit points. And finally, the complement of S is the set SC, which is the set of real numbers that are not contained in S. We have a theorem that goes as follows. The interior, S circle, is an open set. The closure, S bar, is a closed set. And S is closed if and only if its complement, SC, is open. Let's prove the first statement. Let's pick a point P inside of the interior S circle. This means that there exists an epsilon such that V sub epsilon of P is contained in S. We actually claim that V sub epsilon of P is contained in S circle. To see why, let's pick a point Q inside of V sub epsilon of P. We actually need to show that we can find an open set containing Q that is completely inside of S. This is what it means to say that Q will now be in S circle. Well, if we choose our delta small enough, then we see that V sub delta of Q is contained in V sub epsilon of P, which by definition is contained in S, hence showing that there does exist an open set around Q, showing that Q is in S circle. Hence, S circle is indeed open. Let's show the second statement. We're going to do this by taking a look at Cauchy sequences and asking whether their limits are also contained inside of S bar. So let's say that X sub n forms a Cauchy sequence of elements in S bar, and let's let P be the limit of this Cauchy sequence. By way of contradiction, let's say that P is not an element of S bar. What we're going to do now is construct a new sequence of elements Y sub n's contained in S, not S bar, but contained in S, where the limit of the Y sub n's is P. But once we have this, then we'll see that P must be a limit point for S, meaning that P is contained inside of L of S, but L of S by construction is a subset of S bar. So this gives us a contradiction because we can't assume that P is not an element of S bar and then find that P is an element of S bar. We now finish things off by showing the third statement. First, let's assume that S is closed. This means that L of S is contained in S. We'd like to show now that the complement is open. If we choose the point P in the complement, then of course this means that P is not in S. But remember that for every epsilon, if the intersection V sub epsilon and P with S is not the empty set, then we can find some X sub epsilons inside of our intersection. But this would be a problem because then this would show that P is an element of the limit points L of S, which is contained in S, which of course contradicts our assumption that P is an S complement. So this means that there must exist some positive epsilon where the intersection is the empty set, that is V sub epsilon P with S. But then this shows that V sub epsilon P is contained in the complement. So we actually have found a neighborhood around a point P in the complement, showing that the complement is indeed an open set. Conversely, let's assume that the complement is open. We're going to prove that S is not closed. If this is the case, then we can find a point P in the limit L of S where P is not an element of S. Now, for every positive epsilon, we know that we can find an X sub epsilon in the intersection V sub epsilon of P with S. That's because we were assuming that P is an L of S, but P is not an S. However, because P is not an S, P is an S complement. And inside of S complement, we know that it's open. So there exists a positive epsilon such that V sub epsilon of P is contained in S complement, meaning that our X sub epsilon, which was an element of V sub epsilon of P, must be in the complement, which means it is not in S. Of course, this here is a contradiction. We'll end today with an idea that's related to how we started the lesson, that is a statement about examples of closed sets. First, any closed interval is a closed set. Second, let's take a look at an arbitrary family of closed sets. Then the intersection is also a closed set. Third, let's say that we have a finite collection of closed sets. Then the union is also a closed set. We'll show the first statement. We've already seen that if I is the closed interval, then the limit points of I is just I, showing that L of I is contained in I, which is what it means to say that I is closed. Next, let's show the second and third statements. Since each S sub lambda is a closed set, its complement O sub lambda is an open set. De Morgan's laws assert that if we take a look at the complement of an intersection, that's the union of the complements, and similarly, the complement of the union is the intersection of the complements. In particular, if S is the intersection of closed sets, then the complement is the union of open sets. But this is open, so S itself must be closed. Similarly, if S is the union of closed sets, then the complement is the intersection of open sets. But this is open, so again, S must be closed. Thanks very much for watching.